Okay, so I'm gonna today continue where we left off last time. So say a little bit more about the general theory of global gauge fields and their topological properties, and then we'll start studying the Chern-Simons action. So I just wanted to first maybe introduce a slightly easier to understand notation for that we're going to be using in the tutorial today. Suppose I have a UN gauge field, and we can think of it as a matrix. It's an n by n matrix of one forms, Aij, which satisfy they satisfy Hermitian property. Aij plus A bar Ji equals 0. And then we're going to use this notation. If A wedge A is going to be combination combining wedge and matrix multiplication. A wedge A, the Ij component is equal to the sum of A Ik wedge A Kj. Okay, so just like you would multiply matrices, except now we're also including the wedge of one forms instead of multiplying scalars. In this notation, the field strength looks like dA plus A wedge A. And as an exercise, well, where would it be? So the Bianchi identity tells us that d of fa is equal, plus a wedge f of a minus f of a wedge a is equal to 0. So I asked you to do this in the tutorial as an exercise. It's just a little manipulation with this expression. It's not difficult. And let's see. I also asked you to check in the tutorial this afternoon. So it's an exercise that the integral, let's see. So if we vary a, then the trace of f of a wedge f of a changes by d of 3 form. So in particular, if M is a closed 4-manifold, then the integral over this 4-manifold of the trace of f of a wedge f of a doesn't change if we continuously vary a. So I've been speaking so far as if A was just defined everywhere. We have a one form defined everywhere, but if we're being a little more careful and recognize that there can be non-trivial bundles, then we know that maybe this one form A is only defined in local patches, and they're glued together by gauge transformations. But this property, as I'll ask you to check in the tutorial, if A is only defined on local patches, U alpha and glued by gauge transformations. X alpha beta on the overlaps. Okay, so this is kind of a reminder in slightly different notation, but are there any questions about this? Something unclear? Everybody happy? Okay, so it's not really the main focus of this course, but I thought, like, just for the general knowledge of mathematical physics, I should explain to you the terminology people use for these kinds of expressions. So this quantity here, it's something. If I have a gauge field, I'm associating some number which does not change if I vary my gauge field. So it's a topological invariant of the gauge field. And as you might imagine, these kinds of quantities are very important when you're studying gauge theories and in other areas of physics too. So in mathematics, expressions like this are called characteristic classes. So let me briefly explain the basics of the theory of characteristic classes, just so that when you see it again in some other context, you will be familiar with it. So in general, suppose we work on some manifold of arbitrary dimension, and we have a gauge field say A, which is equal to A alpha ij, that's defined in local patches. And it's glued by gauge transformations. So then, firstly, I can consider the trace of the curvature of each A alpha to some power. This is a 2K form, and each U alpha. Now, it turns out, because the A alpha and A beta on different patches are related by gauge transformations, because of the way curvature is a gauge covariant quantity, and I'm taking the trace, which will eliminate the dependence on the gauge, this expression, this 2K form, agrees on the overlaps. So we find trace f A alpha 2K is equal to trace f A beta 2K on U alpha intersection U beta, so that we have a globally defined 2K form, which I'll just call trace of f of A 2K, sorry, K. That should have been K, not 2K. Okay. This is a 2k form on the whole manifold. Next, well, the Bianchi identity implies that d of this expression is equal to 0. So let's see what that's true. Here we have the Bianchi identity. If I try to take the d past the trace, I'll pick up these two. I can trade it for things like this. And it turns out that these terms will cancel by the cyclic invariance of the trace. So let's see this one k is 2, e.g. it's 2, d of trace fa squared is equal to trace twice trace dfa wedge fa is equal to twice trace f a wedge fa minus a wedge fa wedge fa, and that's equal to 0 by the cyclic invariance of trace. So it would not be 0 without the trace, but with the trace, I can cyclically permute this to put this guy in the first position, and then they cancel. So what have we done? We've built for any gauge field, we've built an expression which is a closed 2k form. So that means we can take its class in the RAM cohomology. By definition, the kth Chern character k of A for any gauge field, by which I mean be defined in local patches and glued together by gauge transformations, is the cohomology class of there's some normalization factor, which is -1 to the k, or k factorial 1 over 2 pi I to the k, trace of f of a to the k. And this is an element of h2k of m. So one reason you might want to take this in cohomology is we see over here, in the case k is 2, if I vary my gauge field, this expression changes by d over 3 form. So one way to understand that is to say that the integral over a 4 manifold is an invariant quantity, is constant as I move my gauge field. But another way to say the same thing is that the cohomology class of this does not change if I vary A. So that the cohomology class is a topological invariant of the gauge field. It's constant. It remains constant as I vary my gauge field. So I want you to do that in the tutorial for case 2, but it's true in general. So fact. if we vary A, then trace of FA, the K changes by D of 2K minus 1 form. This is like some completely elementary computation. It's not hard. You can see it in that case. So because of this, the Chern character in H2K of M does not change if we vary A. And there's one more feature of this. So we saw in the case, when we studied gauge fields on the two-sphere with the group U1, we saw that the integral of the curvature of the two-sphere was quantized. It took values in 2 pi times the integers or something like that. There's going to be a similar property in general. This expression here is quantized. So if you are familiar with algebraic topology, the way to say that is actually this lives in the cohomology with coefficients in the rational numbers. But the more kind of physicsy way of saying the same thing is I can ask what I get if I integrate this over a manifold of dimension 2k. And the answer will be some rational number. So if n inside of M is a closed manifold, like no boundary, of dimension 2k, then if we got the normalization right, the integral over M times k factorial of this guy, integral over n, is an integer. So we saw this fairly explicitly in the case of when k was 1. And for the higher dimension, when k is 2 or higher, it's a bit more complicated. When k was 1, this integer was related to the winding number. When k is 2, so as part of the tutorial, I want you to think about how it's related to kind of winding number from maps from the 3-sphere to the 3-sphere, which is also an integer. But in higher dimensions, it's just a bit more complicated. So in the case when k is 2, this is a particularly important quantity because then it's like the instanton number of a gauge field configuration on a 4 manifold. Okay, any questions about this? So as I said, I thought I should just explain this stuff since we're pretty close to it and it's an important thing to know. Okay, so let's get back to Chern-Simons theory, which, as I said, is kind of an excuse to teach you guys what seems to be relevant topics in mathematical physics. So suppose that A is a globally defined gauge field. That is for the trivial bundle. There's just one patch and there's no transition functions relating. There's no gauge transformations on the overlaps. And then if M is a 4-manifold with boundary N, then the Chern-Simons 3-form on N is defined so that integral over N of the Chern-Simons 3-form is the integral over M of trace F of A, wedge F of A. Is the board visible if it goes all the way to the top, or is it too shiny?
It is visible.
It is visible? Okay.
That's one. What was the mystery of the even dimension for the 7-manifold again? I got lost there. Because I felt every time if I have an even dimension, I'm in the complex form. Why was it even dimension again? Sorry. For that to be true.
Why are these characteristic classes always in even cohomology, you mean? Or?
No, you said that the sum if to n is a closed manifold of dimension 2k.
Oh, that's just because the Chern character is defined. I wedge together to the curvature k times, so that's a 2k form. And I want to be able to integrate it over a manifold. So just because I'm integrating an even cohomology class. So you can ask why are characteristic classes always in even cohomology, and it's ultimately it's because the cohomology of the group manifolds are always like U1 is a circle, SU2 is a 3-sphere. SU3 looks like a 5-sphere times a 3-sphere. They always look like a product of spheres of odd dimensions. Okay, so if we want that equation to be true, we need to find a 3-form whose derivative d of CSA is equal to trace of f of a, wedge f of a. So let me explain how you do this. So what we have to do, so this problem can be solved quite easily. So first we have to expand f of a wedge f of a out, and then we'll see how it's d of something. Now, trace of f of a wedge f of a is trace of dA plus a wedge dA plus a wedge a. So that's trace of dA wedge dA plus 2 dA wedge a plus a wedge a wedge a. Okay. Now, it's plausible that we can figure out something d of which will give you the first two terms, because they have a d in them. The last term looks kind of problematic, but fortunately it's 0. So trace of, there's some sign equals 0, because it is aij wedge ajk wedge akl wedge ali. Now, the wedge product in one forms is anti-commutative. So we'll move the last term to the beginning. So this last a, I'm going to move it past these three guys, and I'll pick up a sign. So this expression is equal to minus ali wedge aij wedge ajk wedge akl. And now these two are actually the same with the slightly different indices. Yeah?
How do we know that the gauge field is a one-form?
That's the definition of a gauge field. It's a matrix of one-forms. Okay, so these two guys are the same, except with the indices are given different names, so that the whole expression vanishes. Okay, so that means we can just drop this term here. And whatever the Chern-Simons Lagrangian is, it's going to be something d of which is those first two terms. And now we can guess a nice answer. So we define the Chern-Simons Lagrangian of A to be trace of ADA plus 2 over 3 A wedge A wedge A. And then D of CS of A is, I can move it inside the trace. Well, I'm going to use the fact that D squared is 0, so I won't get a contribution here. DA wedge DA plus 2 over 3. And here, D is going to apply to each of the factors in turn. DA, wedge A minus A wedge DA, wedge A plus A wedge DA. And these three terms are all the same by cyclic symmetry of the trace with this signs from wedging. Wedge A, dA, plus 2 trace dA, wedge A. Okay. Sorry, I shouldn't. 2 dA, wedge A.
Shouldn't there also be a 2 in front of the dA wedge dA?
Well, no, because so D can hit this guy or it can hit this guy, but because D
yeah,
squared vanishes.
0, sorry.
Yeah.
Why all the three are same?
Right. So it's a similar thing to what we did here.
Uh-huh.
So the general rule is the trace is cyclically symmetric, but one form is anti-commute with each other, and one form is commute with a two form.
Mm-hmm.
So if I was to move this guy past those two things, I would pick up a sign. That would be plus. And here, if I was to move this guy, because it's a two form past those two things, I wouldn't pick up a sign. So you can write it out in components, and it will be something very similar to this manipulation. Any other questions?
And why does the middle term have a minus sign to start with?
Yeah, so that's this following fact about the de Rham operator. So if alpha and beta are one forms, then d of alpha wedge beta is d of alpha wedge beta minus alpha wedge d beta. So the intuition, I mean, the sign rules are always that if I move two fermionic quantities past each other, pick up a sign. This operator D, you should think of as a fermionic quantity because it takes a one form, which is fermionic, to a two form, which is bosonic. So if I move it past this alpha, I'll pick up a D. Any other questions?
I'm sorry, I'm being very slow. Why did we pick up the sign again in the middle term?
Here, because I applied D to this expression.
No, I get why the RAM gives me the minus sign, but when I pulled the DA,
Oh, yeah.
do I get a plus?
Because I'm moving, so I'm simultaneously using cyclic symmetry of the trace and the commutativity properties of the wedge. So I want to move this guy over here. So I'm moving a one form past a three form. And that picks up a sign.
I'm sorry, are we passing the two form DA past the one form A?
Oh, did I do some? Yeah, sorry, good point.
Because they're matrices, so you, as matrix,
Yeah.
what you can do is to just pull the last one first, not pull the second first.
Yes, absolutely. But I said
Before S4.
I said it backwards though. I said what we're doing is we're moving this one using the matrices over there. So it moves it past the three form and picks up a sign. And this one here, I'm moving this one over there, and it moves it past a two form and doesn't pick up a sign.
Yeah, you cannot pass the. I just realized you cannot pass the DA of the left, of the middle to the left because the trace exchanges is the one on the extreme ones.
Exactly. That's the only manipulation we're allowed to use is that one.
Yeah.
Yeah. Okay. Any other questions? As you can imagine, you could try to do the same thing with f wedge f wedge f. And you find f wedge f, trace of f wedge f wedge f is d of some 5 form. Well, the Chern-Simons 5 form. And it's a complicated expression. There's a bunch of terms and there's some particular factors. I don't remember them.
So we can do Chern-Simons on every odd dimension by choosing the f of a to the dimension is k to k plus 1?
Yes, there's a Chern-Simons form, and you can add it if you have a Lagrangian for if you're doing Yang-Mills theory in dimension 5. There is a marginal deformation by the Chern-Simons 5 form, but you can't study it by itself. The special thing about dimension 3 is that it starts with a quadratic term, whereas if I was to do dimension 5, it would start off as like a dA dA. So it starts off as a cubic term in dimension 5. Well, if you have a Lagrangian which starts off with a cubic term, you don't know what to do with it. It doesn't define a field theory. Okay, so now heuristically, the Chern-Simons Lagrangian and its field theory for 3-manifold M is supposed to be the integral over gauge fields modulo gauge transformations of e to the I over 4 pi of the integral over m of the Chern-Simons free form. Okay, so what we're supposed to do is take this free form and use it as the Lagrangian for a gauge theory with this particular coefficient, I over 4 pi, which I hope I've normalized correctly. And this is supposed to be a gauge invariant quantity so that I can do the path integral over gauge fields modulo gauge transformations. This expression is supposed to look just like something you might study for Yang-Mills theory, where here I'll put the Yang-Mills Lagrangian. So we should compare to get a very similar expression, but using the Yang-Mills action, which you should have studied in QFT2. So there's something very different about these two quantities. So in coordinates, this is defined by contracting the indices of the curvature using a metric. The Chern-Simons action does not use any metric. One way to say that is the Lagrangian we write down, yeah?
Sorry, before you continue, why are we interested in three manifolds in gauge fields in quantum field theories? Because we usually have four manifolds. So, like,
well, there's many. I mean, well, so quantum field theory is a very broad framework. Its goal, it's that the original goal when people first studied it was to describe scattering of particles. But it's much more broadly defined than that. It describes all kinds of condensed matter systems in various dimensions. It describes statistical mechanics. If you were to if you were to describe the vibrations of the atoms in the table in front of you, it would be a two-dimensional quantum field theory in Euclidean signature, because it's equilibrium statistical mechanics. So that there's like honest physical situations where this Lagrangian appears. The most famous one is the quantum Hall effect. I mean, the reason people were originally interested in studying it, I think Witten's original work was ultimately inspired by some phenomena in statistical mechanics. But later was realized it can be applied to the quantum Hall effect. Yeah, any other questions? Oh, actually, there's another answer, which is kind of fun. Suppose we are studying dark matter, four-dimensional physics. And over here, I include a term in the Lagrangian, which is the integral of theta of f wedge f plus the angle of action, where theta is a quantity called the theta angle. So theta can be promoted to a field, which is called the axion. It's a field which varies and is coupled to the gauge field in this way. So if theta jumps by some discrete amount, so it has a profile which looks like this, then on the interface, the theory you find is exactly this. So Chern-Simons theory really does appear as the interface, describing the interface between two regimes of, say, the interface between two vacua of a four-dimensional gauge theory. So to continue, what does it mean it does not use any metric? So if we work locally, in some coordinates xi, then the Chern-Simons Lagrangian is a three-form. So if we perform any coordinate transformation, then the Chern-Simons form transforms as a three-form. That is, it picks up a Jacobian factor. So in other words, the Chern-Simons Lagrangian is invariant under, so it behaves like a gravitational theory. It's invariant under all diffeomorphisms, just like the Einstein action. Say, well, strictly speaking, orientation preserving. And this is in stark contrast to the Yang-Mills action, because the Yang-Mills action requires this extra background tensor, the metric, which will change under diffeomorphisms. Another source of interest of Chern-Simons theory is going to be explained by some homework which Aldo wrote, that in dimension 3, with a special choice of your gauge group, the Chern-Simons action just is the Einstein-Hilbert action. Like, it is the same as the action for general relativity with a certain cosmological constant. Okay, so given a Lagrangian, the first thing we would like to do to study it is to study its classical behavior, the equations of motion. Well, the Lagrangian is trace ADA plus 2 over 3 trace A wedge A wedge A. Now suppose we vary A. To A plus delta A. Then we can ask what's the corresponding variation of the Chern-Simons Lagrangian. And that is another computation very similar to the ones we've just done. Wow. Trace of delta A wedge dA plus A wedge d delta A plus 2 over 3 delta A wedge A plus A wedge delta A wedge A plus A wedge delta A. So lots of these terms look the same. Like these three terms here, they look like they should be the same. So we're going to have to be a little careful about the signs, just as we were before. What we want to do is manipulate them so that the delta A's are all on the left. Okay? So now, let's say this one. What do we have to do? For this one, we're only allowed to move one from one end to the other, from here to here. And if I do that, I'm moving a one form past two one forms. That gives you a sign of plus. And for this one, I want to move this over here. Also gives me a sign of plus. So for this one here, well, this one here, I want to use integration by parts. So let me rewrite this one first. So trace delta A wedge dA plus A wedge d delta A plus 2 delta A wedge A wedge A. Now for this one here, I want to move delta to the left and this one too. So what do we do? So trace of A wedge d delta A equals minus trace of dA wedge delta A plus total derivative. So you guys are familiar with the fact that when we study the Euler-Lagrange equations, we always make sure the derivatives are not hitting the field like the variation. And this term no, sorry, this is a plus. Yes. That was a plus because it involved moving d past to 1 form 2. So this term here, I can switch them around, the sign of plus. So that's equal to trace delta A wedge dA plus total derivative.
There's a question.
Oh, I'm sorry, yeah.
The way that we arrived to Chern-Simons was always by going to the boundary of theorem for dimensions. So
Yes.
and in that case, well, total derivatives, the integration over total derivatives vanishes because boundaries are closed. Like we do not require any sort of boundary conditions on our variations as we do in other theories. So in here, are we also restricted to these three-dimensional manifolds that are closed, or?
Well, but I mean, we're doing something. Yeah, we'd make the same maneuver when we were studying the Euler-Lagrange equations for a free scalar field. Right? I would vary my scalar field a little bit, and I would find a term where I would hit my variation by the Laplacian operator. But if I assume my variation vanishes near the boundary, my variation is small, it's like localized within the middle of space-time, then I'm allowed to integrate by parts. So the Euler-Lagrange equations are defined for any theory without reference to any boundary condition. Because the variation, I'm always assuming that the variation is localized on some compact set. Okay? The Lagrangian itself, the integral of the Lagrangian, may be problematic because my field might blow up near the boundary, but its variation is always fine. Okay, so if we collect all the terms, we'll find it's 2 of trace delta A wedge dA plus A wedge A plus total derivative. So we conclude so if I want this expression to vanish for any value of delta A, this thing in here must vanish. So the equations of motion state that the curvature so, okay, any questions about this? Yeah.
Yeah, so in the homework I sort of managed to convince myself that that was true. Like when we use the fundamental theorem of calculus of variations and we sort of like try to express everything as a multiple of something that are like linearly independent variations. In the homework I was a bit skeptic that we're not really doing that because the wedge product introduces an anti-symmetry. So is it true that if I have one form which that wedging to every 2 form gives 0. Well, I guess in this case it's different. We have a 2 form which wedge to every 1 form gives 0. Does that give me that the 2 form is 0?
Yes. Because in coordinates, the 2 form in 3 dimensions also looks like a vector, because I can use epsilon ijk to turn it into a vector.
That's how I convinced myself that the epsilon in 3 dimensions could be inverted. But
Exactly.
But if we weren't in 3 dimensions, it wouldn't be clear, right?
Yes, if you weren't in 3 dimensions, it wouldn't be clear. In some other dimension, in dimension D, a 2 form would wedge with a D minus 2 form. But in that case also, if you had a 2 form which wedged 0 with every D minus 2 form, it would have to be 0. Because there's a similar argument would hold.
Okay.
Okay, so I should stop. But you guys might be kind of rightly a little bit weirded out by the fact that the equations in motion tell us the field strength is trivial, because normally, we're studying Young-Wills theory. Maxwell wrote his equations in terms of the field strength, and this guy, electromagnetic potential, was some auxiliary thing that didn't really matter. So here we're saying the actual electromagnetic field is 0. So why isn't it completely stupid and really boring? And the answer is it's almost boring. It's kind of the only things you really measure are exactly these topological quantities we've been discussing. Like you could have an interesting field strength on the 2-sphere. Well, it's a bit subtle. So take that back. You can't have an interesting field strength on the 2-sphere. You can in the presence of some defects. But despite this, there are still interesting measurements you can make. They're interesting quantities. They're just not expressed. There's no local operators, because locally, the only invariants of a gauge field I get are built from the field strength. But there are interesting non-local quantities, such as Wilson lines. So we'll discuss those next time.